In order to answer part A of the Annenberg problem, let's start by figuring out the number of high fare protection seats. We know that this level is equal to the capacity minus the low fare booking limit. In this case, that's equal to 100 minus 50, or 50. We can then compute that into a z-value using the quantity, or the equation 50 minus the mean of 40 divided by the standard deviation of 30. We get a z-value equal to 0.333. Next, we can look this value up in the standard normal loss table, and we get a corresponding value equal to 0.2555. Finally, we can convert this into expected lost sales by using the equation of standard deviation times the L of z, or 30 times 0.2555, which is equal to 7.665. As a result, our expected sales are going to be equal to the mean of the demand for high-priced tickets minus expected lost sales. And this is equal to 40 less 7.665, or 32.335. For part B, now that we have a new normal function with a mean of 60 and standard deviation of 40, we have to figure out the optimal protection level for full price seats. We're going to start out by solving for the critical ratio, but instead of using this in terms of underage and overage costs, we're going to rewrite it in terms of the price of the high fare minus the price of the low fare all over the rate of the high fare. This is equal to 80 minus 40, which accounts for the 50% discount, all over 80, or 0.5. We know that a probability of 50% corresponds to a z-value equal to 0, and therefore the quantity formula simplifies to simply quantity is equal to the mean forecast, which in this case we know is now 60. For part C, we would begin by calculating the same critical ratio, except now the discount is 55% rather than 50%. And so we result in a corresponding critical ratio of 0.55. This is going to increase the z-value into a positive number, which therefore the implication on that is the quantity of high fare tickets will increase because it will be the mean plus z times the standard deviation. When the protection level increases, this means that fewer seats are going to be available for students, demand from whom is abundant. Plus, more seats could potentially go empty if not enough full-price demand materializes. Thus, the expected number of empty seats will increase. Finally, let's move on to part D. Here, we know that the overage is equal to 10 times the cost of underage, basically from this overbooking threat. So therefore, when we're calculating our critical ratio, we can rewrite this in terms of CU over CO, which in this case is equivalent to 10 CU plus CU. That's equal to 1/11, or 0.091. If we look this value up in the Poisson distribution function table with a mean of 8, we get that this value of 0.091 falls between the function of 3 and a function of 4. Using the roundup rule, then, we settle on 4 as the number of seats that we should overbook by.